guess I owe you guys a video or something. I don't know. No? No, it's fine. Okay. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students and this time we have just to meet together and discuss your creation, Lord. In your name I pray. Amen. Is it bouncing? La 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 la. Excellent. So, yes. So last year I took the advice of my brother and I tried to use Rotman's Galois theory book for the first part of this course, and it is a good book, no doubt, but I don't really have time to, it just didn't work out. So not having learned from my mistake, I've decided to use Rotman's Advanced Modern Algebra 2nd edition. There is a 3rd edition which comes in 2 volumes. I do not have that one. But anyway, I have scanned the section I'm looking at right now, and I'll send you guys a copy of it. But so this first section we're going to look at, section 6.1. It starts with rings. I won't even go through that. You already know that stuff. And about 3 pages into the section, he defines what's called a module. So, so for the remainder of the course, for the most part, we're talking about modules, structure, construction, study of their properties, and I mean, this is not exhaustive. There are still tons of questions that are open in the study of modules, just like there are questions open in vector spaces. I mean, people are still writing research mathematic papers about vector spaces, and the same is true about this, but perhaps more so. But basically, what is a module? Here's the definition. And then after I write the definition, you tell me what you think it is. Let R be a ring. A left R module is an additive group oh, and I really should emphasize there abelian, and we're going to call that group M, equipped, all right, with a scalar multiplication which is a map from the Cartesian product of R and M to M again, denoted by R comma, R comma M maps to Rm. So we use juxtaposition to denote the scalar multiplication usually, such that, so one of your questions probably should be, well, such that the following, such that for all M and M prime in M, and all R prime in, of course, 1's not a variable, but that's the unit of the rings. We are working with rings with unity here. Not necessarily commutative, though, at this point. All right. All right, so something I should have emphasized, I said in words I didn't write yet. I mean, I've laid the groundwork for this idea in our 421 course, but I have told you at some point that if you say an additive group is non-abelian, that's just not friendly. And anyway, so here's the rules. Number 1, R times M plus M prime equals, you fill in the blank, 2 R plus R prime times M equals, you figure it out. Number 3, R prime parentheses times M is equal to, well, you figure it out. And part 4, arguably the best part, 1 times M equals to, well, you figure it out. And so we often denote a left R module M by, so this, he says sometimes, and when he says sometimes, I think he really means almost never, by like this, RM, the shorthand for left R module. So you guys, we can fill in the blanks together, right? You know what's going to go here. This is going to be RM plus RM prime. This is going to be RM plus R prime M, right? This is going to be R prime M parentheses moved. And what should 1 times M be? Wow, you guys are taking a certain posture today in my questioning. I kind of like it. It's very, I'm not sure if it's arrogant or apathetic or a little bit of both. Mostly arrogant? Okay. I won't tell. Yes, so these are unsurprising. Why? What is this? What is this definition I just wrote, actually? So I guess my initial comment would be, I'll put it up here, remark. If R is a field, then Rm is a, what? Yeah, vector space over the field, right? So calling it a scalar multiplication seems like pretty good terminology. I mean, this is a generalization of scalar multiplication as it relates to the linear algebra class, of course, because the linear algebra class assumed that the scalars were from a field. Except for the first part of the course where I misbehaved and worked out things over an arbitrary commutative rings. You're not supposed to do that in linear algebra. That's just me misbehaving. But with good cause, right? Because now we've actually proved a bunch of things about modules already in your 321 class, if you go back. Right. We haven't done things, though, if you look at it, there's places we stop short in linear, right? I might have assigned a homework problem about how to solve equations over like Z6. But we never really fleshed out, how do you solve equations over a module, right? If you have a set of equations, linear equations perhaps, with variables taken from a module, how do you solve that set of equations? What are the rules for that? How does that work out? That's one thing we'd like to understand eventually. That's actually fairly far down the road here. As we study modules, we'll first study them as a vector space, essentially, studying their abstract properties, their natural mappings, their homomorphisms, their isomorphisms, quotients, then leading to something called the tensor product of modules. And then after all of that has been sorted out, eventually we'll get back to solving systems of equations over module. That's like the very end of the course, which if I play my cards right, should lead us to like a proof of the Jordan form and some other things like that as a special case of a more general procedure. Anyway, any questions about this? All right, so we could also talk about sort of the other hand, so to speak, what do you want to call it? I can't count. 1, 2, 3, I just can't. What if I had m plus m prime r, m times r plus r prime, m times r prime, and m times 1. Well, you know what's going to happen here. That would be mr, m prime r, mr plus mr prime, mr r prime with parentheses rewritten, and of course m. Right. This would define the structure of a right R module. And I guess if there's any justice, surely he must use this as the Yes, in fact, that is his example for that. Now, so what are examples of? So can you guys think of any examples of these? Obviously, a vector space over a field with, and I'll use the language V. The point set is the set of vectors, right? The ring is the field. So any any vector space that we have previously discussed is a module, right? What else? How about an abelian group? Okay, so abelian group. What would the scalars be for an abelian group? I mean, I'll start you out here. The point set is going to be the group itself. The ring, fill in the blank here. All right, so we need something like R times M makes sense, right? I mean, instead of using M, let me say RG. Makes sense. And instead of, actually, so it's kind of funny, but I mean to make contact with my usual intuition. I kind of have to switch the letters around here a little bit because my scalars I usually use M and N for, you know. And I mean, this is mg plus ng, right? For all m and n in the integers. Oh, I guess I just wrote. What's that? Yeah, so this should be the scalar multiplication. What's right? And then the integer 1 times a group elements, just a group element again, so forth, right? So in fact, R is equal to Z. So this is, in short, why we can say that an abelian group is in fact a Z module. So Z module is an abelian group, and in fact, those are interchangeable. All right. The third example he gives here is, and by the way, we're on page 397 of Advanced Modern Algebra by Joseph Rotman. And let's see here. So, oh, by the way, I'm not saying that Dumb and Foot isn't worth reading. In fact, it is worth reading. It's just I like the flow of this text for a lecture a little bit better. It allows. I mean, I think this one section has about. I believe it's got a bunch of sections in Dumb and Foot kind of woven together at a somewhat like a digestible amount of information. It'll take me a while to get through this section, but having gone through it, I think we'll be satisfied with the content in this section. It's a good path, so I'm going to follow it. Anyway, so his third example here, every commutative ring is an R module over itself, right? So this is kind of familiar. So if you just take M equals to R and an R equals to R, so to speak, and just define the scalar multiplication to be multiplication of the ring on itself, that also defines an R module. So any ring can be made into an R module with respect to its own multiplication. If you have a subring, you can make it into it. If you had S as a subring of R, you could make the ring into an S module, right? For example. This is not unlike our discussion of vector spaces, right? Any field is a vector space with respect to itself. And if you had a subfield of that field, that the given field is a vector space over that subfield. We've seen that again and again in our study of extensions, actually, right? So one is a subcase of three. Yes. the very special case of 1, but yeah. Okay, and then finally, let's get to something that really requires. Now, this right here, this is a pretty severe jump in terms of concept. The next example I'm about to give you is maybe not as trivial. Yet it's not hard, but this is one of the constructions which is just so important to this arc of the course. Okay. So this example we'll come back to again and again and again. So let T from a vector from V to V be linear transformation over V with the dimension of K, V being less than infinity. All right, so here, K is a field. All right, so we're talking about vector space V over the field K. Usually he uses K in here for a field. And what he says is that the vector space V can be made into a KX module. We can view V as the module over R equals to polynomials with coefficients in K of X. All right. So the vector space V can be made into a KX module by defining the scalar multiplication as follows. So if we have f of x is equal to a sum, all right, I equals 0 to m of, let's say, ci x to the I, all right, where, of course, the c sub i's are scalars in the field in this case. And what I'm saying is that this polynomial is a scalar in this fx module, right? So what we have to define then is, what does it mean to have f of x scalar multiply a vector v, right? So what do you guys think? How would you define the action of a polynomial on the vector space in this context? We need to have these axioms over there to have a module. I'll get you started. Sum I equals 0 to m. And I'll do the CI for you. There you go. What do we do with that x? How do we convert x, to the power I into a vector? It doesn't have, it can be a different vector for each I, of course. In fact, it will be. But here's what we do. We let that be t to the power I acting on V. We may or may not actually write those parentheses. No, he does for now, at least, yeah. With the understanding, of course, that this is meaning what? This is like C0 plus C1t plus plus Cm t to the power m. That operator acting on V. So in other words, t to the 0 power is the identity operator. T to the 1 power is just t again. T squared is t composed with t. T to the m is t composed with itself m fold times. M minus 1 fold times. Sorry. Yeah. And so check it out. Does that give V the structure of a module over the ring of polynomials with coefficients from the field? Certainly if you have the sum of polynomials, it's pretty easy to see that this definition is going to have the right distributive properties, right? So axiom, let's see here, axiom 2 right? Axiom 2 is going to come from just basic polynomial arithmetic, essentially, right? That you add coefficients and so forth. Axiom 1 for the modules, that's going to come from the linearity of linear transformations and their higher composites, right? That the composite of linear transformations is linear. How about 3? Why is that true? Yeah, yeah, let's see here. So it'd be like f of x times g of x, right? That would be my RR prime acting on V is allegedly going to be equal to, well, oh yeah, but it's supposed to be f of x multiplying g of x on V, right? Now, I gotcha. So you're saying that this, well, this is, let's say, h of x, right? Some polynomial. That acting on V, of course, is essentially h of t. See, this, I was rather explicit here, but of course, you could rewrite this as just f of t acting on V, right? I mean, it's just that. And so, yeah, if the product of this is h of x, then by definition, that's h of t acting on V. On the other hand, this is what? This is f of x acting on g of t on V, right? Which is then f of t acting on g of t of V. And by composition of functions, those are equal, right? Well, it's a little bit more than that, I suppose. It does have to do with the fact that, I mean, if k was not commutative, we'd be kind of in trouble. It's important that we're taking polynomials over a field here, so that multiplying these is the same as composing those. I feel like you could get into trouble in print. I don't know. Yeah, I'm a little.
Yeah, I would probably just using some implicit details.
Yeah.
Algebra.
Right. But in any event, some details aside, it should be intuitively clear what we're doing is reasonable. I mean, it also should be also reasonable to you that for a given vector space, how many different fx modules are there? Like I say, R3 is a module over polynomials. You should be like, that's great, but there's infinitely many choices for an endomorphism of R3, right? For a linear transformation on R3, right? This module somehow encodes what? It encodes the structure of the linear transformation, right? So yes, this makes V into a fx module, but this fx module is very much studying the structure of the linear transformation T, right? In a way which I think if we introduced it in the previous course, right? Well, if we introduced it in 321, people's brains would heads would explode, right? I mean, if I introduced this idea, it's really out there, isn't it? I think it's pretty out there. Now, this has a notation. This whole construction is VT. So V viewed as a fx module as is induced by the linear transformation T on V. Okay. And we can also talk about n tuples over the field, right? With A here being an element of kn by n, right? This is very much related to our previous example. You can look at the module induced from a given matrix on n tuples over the field, right? So and I'm still not being. Let's see here. So he says this is a special case really of part 4. Is if we let A be an n by n matrix with entries in k, let T from kn to kn be a linear transformation. So here we're we're just thinking about T going from Kn to Kn.
We're using lowercase k first.
Yeah. With T of V equals to AV for all V in Kn. So that, of course, would give us a module of column vectors in K, and right. He says that, well, little theorem, which is that Kn to the A is equal to Kn to the T. Now, I guess I haven't really defined what is Kn to the A yet here, so that doesn't seem like a very good theorem. I mean, I'm having trouble even understanding what I mean by that at the moment. Let's see here. But I think you could tell me if what would the analog of what's in red be for if I take fx acting on V, where V is a element, so this is polynomial in K. This is a n vector over K, right? And I want to give a definition of how to act on the vector by this polynomial with respect to the matrix which is given. How would you do it? Let's, here I'll just 0 to m, ci x. Suppose that this is my polynomial explicitly. I'm acting on the vector. So what is it? You guys, I think if you're starting to get the idea here, we just replace this with a to the power I, right? And so that's what we mean by this module. The difference would be, let's see here, the abelian group that we're working on, the M is just n vectors over K. The ring is still polynomials in K. The difference, of course, is just that we're defining the scalar multiplication by a sum of powers of the matrix as opposed to by the given linear transformation. So this is the usual song and dance. We can either look at transformations or we can look at matrices. And of course, in an abstract vector space, if we pick a basis, we can still trade our transformation scalar multiplication for a coordinate-based matrix formula. Yeah.
So what are some examples? What would be an example of this?
So we will come back to this as we go on and study it more deeply. Giving you just a brief glance ahead, what we'll learn, one of the main things we'll learn is that we can also study submodules of a module, right? And when we study submodules, we'll find that there's a correspondence between submodules of this module and what are called invariant subspaces of the transformation. But you guys may remember that the invariant subspaces of the transformation correspond to a special choice of basis which decomposes the linear operator into a block diagonal form. So it turns out the study of submodules of a given module is intimately connected to the problem of decomposing a matrix into blocks. Now, his example 5, he says, is a generalization of 4. Let K be a commutative ring. Let me just write it down. I'll write it down over here. So this might scratch the itch that's bothering you, Sam, this here. So let K be not a field, but a commutative ring. All right. and M a K module, and phi from M to M a K map. What would that mean? What would that mean, a K map? I think that's defined in the first part of this section, which you guys, of course, would be impossible for you to have read since I didn't share it with you, nor tell you I was going to do this today. So, but if you had to guess, what would it mean, a K map? I would think that it would mean that multiplication by some element of K. I would think that it must mean, well, let me not speculate. I think it's a ring homomorphism, but I'll tell you, I'm just going to put a little question mark right here as to what precisely is meant by that. But this much we can say is, how are you going to define the this here? So if I have f of x, right? F of x, I want to let it act on M. I need to give a definition for that, right? I mean, sort of the glib definition would be this. It's really just f of phi acting on M. To be more specific, this fx is, c0 plus c1x plus c, let's say, I don't know, r, x to the power r, acting on M. So that should be, by definition, c0 on M plus c1 phi of M, cr, the rth power of phi acting on M. So it's the same thing we just did in example 4, except instead of, we were not assuming that phi is a linear transformation because M is just a K module, right? So it could be, for example, an abelian group. And it could be that K is the integers, It could be a lot of different things. K is a commutative ring, not a field in example 5. So. Any questions? No? All right, so he has some, I think he may actually give the definition. I think he may have just used this term and then defines it like a page, like in the same page a little bit later, just because it was convenient to use the terminology here, but not convenient to put the definition before here because it breaks the flow. But in defense of Rotman, I have not read all 398 pages up to this point. It may very well be that on page 50 he has a half-page discussion of K-maps. That's typical of his writing. He doesn't do things all at once. He scaffolds things and comes back to topics and adds layers to them as he goes on. That's his writing style. So, anyways, definition. Definition, if R is a ring, M and M both are modules, right, or say both left or right, but suppose both of them are the same, either they're both left or both right, okay? Yeah, the same parity, same handed, I don't know what you want to call it. Then F, a mapping from M to N, is a R homomorphism or R map. Aha. So here, K map being defined actually. If what? We need, first of all, we need the additivity. F of m plus m prime is f of m plus f of m prime. 2, that f of Rm is equal to Rf of m. Right? This would be the left one, or in right case. What would the rule be? That we can pull R out like that, right? That would be the natural assumption there. And that has to hold for all m prime and all R. If an R homomorphism is a bijection, then it's a R what? R isomorphism, right? And we say that the modules m and m are isomorphic in that case, all right? So he says, note that the composite of R homomorphisms is an R homomorphism. And if F is an R isomorphism, then its inverse function is likewise an R isomorphism. So the things we said about composites of linear transformations and isomorphisms are still true in this context. Right. And he has a few examples. He says, if R is a field, then R modules are vector spaces, and R maps are linear transformations. Isomorphisms are non-singular linear transformations in that context. Example 2, Z modules are just abelian groups. And he says lemma 1.58 shows that every homomorphism of abelian groups is a Z map. That would be the thing that we discovered in abstract algebra 1, that essentially what happens to one fixes the action of a homomorphism. I mean, the law of exponents essentially says once we do something to one for an abelian group, then that kind of, if you think about it, fixes everything else. I think we've seen that lemma in the previous, the fact that a homomorphism of abelian groups gives a Z map. That's essentially just the way laws of exponents filter through a homomorphism in the abelian case. Then his example 3, he says if you have a left R module, you can look at multiplication by R, also known as homothetty. Homothetty, multiplication by R. So I've given you homework exercises studying this thing more than once. So mu R, his notation, mu R mapping from M to M by mu R of x equals to Rx for all x and m. So here, I'm saying M is a left R module in this discussion, okay? So that's an example of an R map, okay? So left multiplications give R maps. And then finally, a proposition. Well, his example 4 actually leads to this proposition. If we look at the R module built over the linear transformation, the question is, okay, so his example 4 basically shows that if we pick a basis, all right, if we pick a basis for the vector space, all right, and we look at the corresponding kx module built from multiplication by powers of the matrix, then that kx module is isomorphic to this kx module. All right, so if you pick a basis, then the corresponding matrix module is isomorphic to this module.
And that's the theorem you wrote.
That's yeah. That actually is just literally they're equal, because in that case V was equal to Kn. Now I'm saying suppose V is an abstract vector space. Pick a basis, construct the corresponding module over n vectors. Well, then that matrix multiplication module built on n vectors is isomorphic to this abstract kx module built on the abstract vector space as induced from linear transformation T on V. But those are still isomorphic. And then that ultimately leads to proposition 6.11, which I'll stop with today because I think it's a good stopping point. And this says if we have V, what time is it, guys? 9:08. Okay, I think I can, we're okay. If we have V over K, and you have T and S linear transformations on V, all right, then the Kx modules, all right, V upper T and V upper S are Kx isomorphic if and only if there exists phi from V to V an isomorphism, and with S equal to phi T phi inverse. So this is proposition 6.11, which I'll probably start with the proof of next time. Or if I get my act together, maybe I'll post a video of it to make up for my many transgressions and getting here late and missing the whole day. But this is very satisfying because it essentially says that, you know, it's just a change of coordinates that gets you from one module to another, right? And so isomorphic modules is yet another way of saying, yeah, this is really the same linear transformation. It's just recast in a different sort of coordinate system. Anyway, I'll stop there, guys. Thanks.